As Kurt mentioned, my name is Michael Poston, and today I'll be talking about some work that Greg Greaves and I at Georgia Tech have been doing in collaboration with all these other wonderful people with some slides. The work has to deal with hydroxyl formation and diffusion within the near surface of a lunar regolith grain. The speakers before me have given a great overview of all the discoveries pointing towards water existing on the moon, so I won't go into them in any depth at all. But one thing that hasn't been mentioned is that these discoveries have led to consideration of a possible water cycle on the moon, involving several different origins for the water, what sort of evolution goes on with the water that is there, and then where does this water end up? Is it lost? Is it trapped somewhere? That sort of thing. So today we're going to focus on a solar wind implantation source, radiation chemistry, and then the retention of the hydroxyl that will be formed by this radiation chemistry in the lunar regolith itself. And I just mentioned that hydroxyl is important. It's a piece of this water cycle on the moon because, as Dana mentioned, it can react by recombinative desorption to form water and possibly hydrogen as well. And then secondly, hydroxyl itself is a reservoir of hydrogen seen at all latitudes that can be extracted for use as a fuel or life support for lunar surface operations. A brief note on the scale of the model that I'll be using today. There's definitely processes that need to be considered at all of these scales, such as migration from grain to grain on the millimeter scale, or the effects of gardening on the centimeter to meter scale. But today I'll be talking only about what happens inside a single grain, and even more specifically inside the first couple hundred nanometers of a single grain of lunar soil. So to start out with this process, we considered just a situation where you force all of the hydrogen when it comes in to stay on the very surface, the vacuum interface, where it can then find other hydroxyl groups, get close enough and react together with enough energy to form water or hydrogen, and then that will desorb immediately and begin migrating. So the process overall is protons in, forming, in this case, a surface hydroxyl, and then eventually, with enough energy, recombinative desorption as water or hydrogen. So using this very simplistic model, we came out with an activation energy of 14 kilojoules per mole, which some of you might realize is pretty small, but we're not going to worry about that being very small for today. That'll come in the future. And this matches the distribution that was published by McCord and the M-Cube team, so we're done, right? Well, no, as I mentioned already, this is way too simplistic. It's known, there's posters here at this conference, in fact, and I believe speakers before me have mentioned that the protons will penetrate past that vacuum interface and be implanted at depth. So, accounting for that, we assume that the protons are all about 1 keV, and they'll implant to about 15 nanometer depth. And then how do they get to the surface to undergo the recombinative desorption that we're interested in exploring? Well, there's diffusion, as Dane also mentioned. And then in our model, when you get to this green stripe, that's where we allow the hydroxyls to undergo the recombinative desorption. And also as a note, in this form, we decided to go ahead and start adding in other other important processes like photon stimulant desorption. So here we have the same schematic that I gave before, except you might notice now we have the hydroxyl inside the near surface region of the grain. So for those who care about the reactions, here they are. We have protons coming in and finding trapped sites represented by Y. In this model, if there isn't an available trap site, the proton is rejected immediately and we stop caring about it. Once you have hydroxyls formed, there's diffusion, and this is dependent on the second derivative of the distribution. So in a symmetric distribution like I have here, these arrows represent that there will be equal diffusion in both towards the surface of the grain and into depth, which will become important in a couple slides. Once the hydroxyl gets to the surface, as I mentioned, we have photon-stimulated desorption, which is dependent on the flux of the photons as well as the concentration of hydroxyls at the surface. So this is going to be highest probably around noon when the photon flux is highest. And then finally we have the one we're really interested in, recombinative desorption, where these two hydroxyls on the surface get enough concentration that they're near each other and they get some energy from temperature and desorb as water or hydrogen. And this is dependent on both the temperature, material parameters, and the second order concentration. So it's a second order process, basically. So what were we naively expecting when we went into this? Well, we thought that the higher temperatures at low latitudes would make the diffusion to the surface very fast, and then the reaction, the recombinative desorption at the surface very fast, and this would more than make up for the fact that there's a lot more protons coming in at low latitudes as well. And so as it turns out, that is not the case. While there is greater diffusion to the surface at low latitudes because of temperature and greater loss, there's also burial of the hydroxyl that goes into depth, and there's no processes that we're considering that can remove that hydroxyl, so it's there to stay pretty much. And the 3 micron band, or the 2.8 micron band that's being used to detect this hydroxyl will go into the surface on the order of micrometers, whereas here we're considering 0.2 micrometers, or 200 nanometers of depth. So all of this hydroxyl will be seen by the spacecraft. We found some depth profiles for a returned Apollo grain, and it's intriguing to see that this diffusion, while it doesn't give us the right distribution to match the spacecraft, does give us the right depth profile to match what was seen for hydrogen coming out of the lunar grain in laboratory studies here on Earth. So what can we do to get back to a situation that matches m cubed results? Well, we can say, well, let's take this recombination and say maybe because of the radiation environment, it's possible to have this recombinative desorption, which all the literature tells us only happens at the actual vacuum interface. Well, let's say there's a chance that it can happen inside the material and not immediately dissociate and go back into the crystal lattice. So we allowed a chance for recombinative desorption to occur at depth, and it's exponentially decreasing, so it's still just as likely at the surface, and there's a probability that if the equations for the recombinative desorption say it should happen, there's a chance that it will happen rather than recombine. What does this do for us? Well, if the clicker works, there we go. It gives us back a shape that matches m cubed. So this is encouraging. If we wave our hands enough, we can get back to the right distribution that matches what's been observed by the spacecraft. So, as I mentioned before, this might be possible if there's certain radiation chemistry going on, and we are actively looking for reactions in the literature that will back up this sort of process on the moon. But we don't want to give up on diffusion just yet. So thinking about radiation, we went into the literature to look for radiation-enhanced diffusion, and turns out that there is actually precedence in the literature saying that high amounts of radiation damage are potentially able to increase diffusion rates quite a bit. There's also some materials where it decreases the diffusion rate in low doses. But high doses, quite a bit in some materials, and no one has done this to my knowledge on actual lunar relevant minerals or lunar samples. So for now, we're just saying, well, what if this does happen on the moon with this radiation environment? What will happen? So we left everything the same as my original diffusion scenario, except we took the diffusion coefficient and increased it in the region of the grain that will be most heavily damaged by the radiation. This will have a net effect of making the push towards the surface itself for diffusion greater. So instead of having a symmetric distribution move symmetrically, there's now a preference to go towards the surface itself. So some more depth profiles, which I didn't mention before. It's concentration on the y-axis and then depth here on the x-axis. You can see that on the right where we have this anisotropic situation, this landscape where we have a varied diffusion pushing towards the surface, we do have a decrease in our total concentration of hydroxyl that's built up at the equator compared to the flat isotropic situation that's shown on the left. However, if we integrate these curves, you can see that the equator still builds up the most hydroxyl at sensing depths rather than higher latitudes being dominant. So this change we did that pushes the hydroxyl towards the surface still isn't enough on its own to explain things. However, and then if we do a distribution of latitudes, you can see this is definitely not a shape that matches m cubed. But because we have this shape that matches the depth profile from the literature, we decided to look at whether or not our model supports a diurnal variation. So here I have plotted the 100th day of our simulation, and each of these traces that's pretty much overlapping on all these graphs represents a time of day. And I'll integrate them on the next slide. But right here I just want to draw attention to the fact that these don't change visibly at all on this scale. So the high latitude would have a very small diurnal variation, but the low latitude in the isotropic, the flat situation, has a small but noticeable variation on these graphs. And the anisotropic, the landscape or surface preferential diffusion, has a huge variation throughout the day. What does it look like with the integrations? This starts at dawn, right here on the left. And so in the morning, it builds up a little bit until the temperature reaches the point where the diffusion and the recombinative desorption dominate over the implantation rate. And then we lose concentration throughout the day until in afternoon the temperature drops enough that the implantation rate starts dominating over the loss rates again. So just to bring it all back together, we have the oversimplified diffusion model, or no diffusion model, which does get the distribution that matches the spacecraft, but is not really physically meaningful to us at this stage. If we add in more physical meaning with implantation at depth and then diffusion to get back to the surface, this gives us a distribution that's inverted compared to what the spacecraft saw. Because the higher temperatures do increase loss rates, but also increase barrel rate and trapping, but still within a depth that the spacecraft will see. If we allow for some loss at moderate depth, this does bring the distribution back to something that matches the spacecraft, but we haven't identified what chemistry would make this make physical sense yet, and we are still working on that. Altering the diffusion landscape to this surface preferential situation due to an assumption about radiation chemistry increasing the diffusion rate does give us, or pushes the distribution a little bit better than just a flat diffusion landscape has, but it's not enough to match the spacecraft. And then finally, the parameters and processes we considered here, which, so in reference to the question on the previous talk, yes, there's definitely other processes going on that we haven't considered. But what we've considered here does provide a diurnal variation in OH concentration and does give us a depth profile that matches what has been seen on a returned sample. Thank you.
Larry Taylor?
Yeah, very good, Mike. I like that. One thing I want to point out, and that is that there was a paper by Fegley and Swindle in 1993 called Resources Near Earth Space. And in that paper, they show the different fluxes that you get. And when you're at the equator, your flux is very, very low compared to many other places because you're in the magnetosphere, okay? And that's really affecting things. So that's another factor you have to figure in, is that it's not just temperature dependent, but it's also flux dependent.
You're referring to the solar wind proton flux? Or, okay. So you're considering if we're looking at the near side only in this situation? Because for the equator on the far side, of course, there won't be a magnetosphere at that time. Okay. Thank you.
Quickly from Gordon.
How does porosity on the surface affect any of the depth penetration or scale lengths that you're doing in this analysis?
The only porosity consideration we've taken into the model at this point is that there's an effective enhancement of surface roughness, where you actually have much more surface available than a flat sphere for the moon would cover.
How would that affect your calculations?
We do. So you're asking how it would affect the calculations?
Yeah.